An earlier film in this series suggested how the concepts of force and motion might be developed experimentally in a school situation. The film ended by considering Newton's first and second laws of motion. In this film, I'd like to develop those ideas and to introduce interaction, the forces of action and reaction. And I'd like to show you some of the apparatus that we can use in school for illustrating Newton's third law of motion. Interaction, then, or action and reaction, can be illustrated by some very simple apparatus, such as the playground trolleys we have here. I'm first of all going to ask the boy, that's the one over here, to hold the rope tightly and the girl to pull on the other end of the rope. And we see that the two vehicles come together right in the middle here. Now if we repeat this experiment, and this time I'm going to ask Amanda to hold the rope tightly and Oliver to pull at his end. And again we see the two vehicles come together in the middle. And if both had pulled at the same time, again, both vehicles would have come together and met in the middle. Action and reaction can be illustrated in several other ways. For example, by using two horseshoe magnets. The magnets are mounted on two trucks which run freely on the railway lines. I'm going to push the two magnets together and release them at the same instant. They fly apart to approximately the same position, thus indicating that action and reaction are equal and opposite. For this experiment, I shall use a friction-driven car and some polystyrene beads sprinkled on the bench. And then on top of these beads, I place a piece of cardboard to act as a roadway. So rev the car up and place it on the roadway. This experiment shows that the car exerts a force on the road and the road exerts a force on the car. I'll try again. Now, I wonder if you'd help me with the next experiment, please. I'm now going to use a sparklet bulb, which is a small cylinder of carbon dioxide, to illustrate action and reaction. I'm going to insert the cylinder in the end of an aluminium trolley and pierce the end with a center punch. Now, Oliver, could you hold the end of, just hold the trolley for a minute, please, will you? I hope that experiments such as these you have just seen will convince pupils that forces occur in pairs. That is, that a force never exists on its own. And so we now turn to collision processes. I would like pupils to investigate the collision between two bodies for themselves. Perhaps the simplest way to do this is for them to use trolleys such as these running on a friction-compensated slope. In this way, they can ignore the effects of friction altogether. We friction compensate by using this screw adjustment at the end of the runway. We use each trolley as a unit of mass. A needle in one trolley sticks into a cork in the other so that they move off together. We're now going to use this ticker timer to find the velocity of this trolley before and after it collides with a stationary trolley. We can see that the collision took place here. So we'll measure the distance gone in 10 ticks before the collision. And then the distance gone in 10 ticks after the collision. By measuring those distances, we find the velocity before and after the collision. The actual results obtained by one group of pupils are shown on the board. 1 unit of mass and 21 units of velocity before the collision, and 2 and 10.4 after the collision. Having done this experiment, I should ask the pupils to repeat it, but this time to use 2 trolleys stacked like this. In this way, we have 1 unit of mass before the collision and 3 units of mass after the collision. Finally, I should ask them to stack 3 trolleys on top of one another. Now we have 1 unit of mass before and 4 units of mass after the collision. For the same group of pupils, the results they obtained were as shown here. 1 and 27 before, 3 and 9.3 after. And finally 1 and 31 and 4 and 8 after the collision. Well, having got these results, I should ask the pupils to study them and to see if they can see anything significant about them. And I should hope that they discover for themselves that the product mass times velocity is very nearly the same before and after the collision in each case. And then I should say, well, this product, mass times velocity, is so important that we give it a special name. We call it momentum. We can now use trolleys to investigate elastic collisions. One trolley, fitted with a spring-loaded plunger, runs down a friction-compensated slope and collides with another trolley of equal mass. The speed of each trolley is measured by a ticker tape, the 2 tapes passing through the same timer, which is fitted with 2 carbon paper discs back to back. The first trolley came to rest, and the second trolley moved off at the same velocity. We have not as yet discussed the vector nature of momentum. For this, I'm going to use a trolley fitted with a spring-loaded plunger. The plunger can be released like this. I shall again use the ticker timer fitted with 2 carbon discs back to back and 2 tapes to measure the speed of the trolleys as they fly apart. I would now ask the pupils to repeat this experiment, this time with 2 and then with 3 trolleys stacked on top of each other on one side, like this. In each case, we started with no momentum and ended up with the same numerical value of momentum on either side. We asked the pupils how this can be possible, and this leads on to the idea of momentum as a vector quantity. If you have an air track, such as this, you can demonstrate the conservation of momentum more accurately. Air from a vacuum cleaner is blown into this tube, in which holes are drilled along the top and the sides. A perspex vehicle then floats on a cushion of air, rather like a hovercraft, so that there's practically no friction. To find the speed of the vehicle, we attach a drinking straw to it. The straw is then photographed stroboscopically using a camera with a rotating disc in front of the lens. The disc is operated by a synchronous electric motor. We can now investigate inelastic collisions using 2 vehicles of equal mass, one of which is fitted with a needle. This is what the stroboscopic camera sees. To show up the drinking straw more clearly, I would place a black screen behind the track. Here's a photograph taken in this way. By measuring the separation of the lines, we see that momentum has been conserved. With these two vehicles, we can investigate an elastic collision between two bodies of equal mass. Here again is what the strobe camera sees. The resulting photograph looks like this. To investigate a collision between two vehicles of different mass moving in different directions, we're going to use this shutter. As the vehicles come together, the strobe camera will photograph the top part of the straws, and as the vehicles separate, the camera will photograph the lower half of the straws. Two units of mass will move in from the left, and 3 units of mass from the right. This is the kind of strobe photograph produced during this experiment. By analyzing it, we can find the total momentum before and after the collision. In addition to using these photographs to measure momentum, they can all be used to find the kinetic energy before and after each of the collisions. So far, we've considered collisions only in one dimension. With this apparatus, we can investigate collisions in 2 dimensions. First, we should clean the glass plate with methylated spirits, and then level it up using a rubber wedge in each corner. The magnetic ring puck is filled with dry ice. This evaporates so that the puck floats on a cushion of carbon dioxide. The pucks can collide elastically. If I place one puck at rest, we get a collision like this. A camera, in this case a Polaroid camera, and a rotating disc enable us to take a stroboscopic photograph of the pucks. The photograph obtained can be analyzed to show conservation of momentum and kinetic energy. Having established conservation of momentum, let's see if we can use it to find the speed of an air gun pellet. I'm going to fire the pellet into this block of plasticine, which should start the truck running down the friction compensated slope. We know the mass of the pellet, and we know the mass of the truck and the plasticine. So we can find the speed of the pellet by finding the speed of the truck. This I'm going to do by timing it over 1 meter. 3 seconds. This particular experiment gives the velocity of the pellet as 150 meters per second. We might now confirm this result by direct measurement. In radioactivity experiments, we use a scaler, but this instrument can also be used to measure short time intervals. This one has a 1000 cycle oscillator in it, which enables us to measure time to 1,000th of a second. When this circuit is broken, the scaler starts counting, and when this circuit is broken, it stops. I've placed a piece of aluminium foil across each of the gaps. These should be broken by the pellet. In this way, we get a direct measurement of the time taken for the bullet to travel 1 meter. The pellet took 6 milliseconds, which gives it a velocity of about 170 meters per second. In this film, I have demonstrated several trolley experiments. Of course, in the Nuffield scheme, we would expect the pupils to do those experiments, so that they might have a better understanding of momentum. The gun experiment, which teachers themselves would demonstrate, enables pupils to see that this concept of momentum can be used to find the speed of a pellet. And when this is confirmed later by a direct measurement, we hope that for them, physics really does make sense.